Hello, I'm Jerry Brinkley, and this is the Boyles Law Group. My partner is Joseph Carpenter. The original process. Boyle worked in the Royalty Society of London in the 1660s, where scientists began emphasizing where carefully measurements and repetition in experiments. He and Robert Hooke, who was his assistant, Robert Hooke, built one of the first precision instruments for studying gases. Boyle performed his experiments at a constant room temperature to isolate the effect of pressure on volume. He compared results several times to ensure accuracy, an early example of scientific reproducibility. And the bottom right is Boyle's Law. It's just a little example of one of his experiments. Original difficulties that he faced is the handling of mercury. Mercury is not only heavy, but it's very toxic. It takes more than one person to work it. The tube is tall. Boyle couldn't reach it on himself, so he needed his assistant Robert Hooke there to help hold, seal, and fill the tube. Keeping the apprentice upright and stable required coordination and careful setup between the both of them. Boyle had to connect his measurements to an invisible concept, air pressure, gas behavior, which people didn't fully understand yet at the time in the 1960s. Original motivation. Hooke's contribution. My partner did it over Boyle's contribution. I'm doing it over Hooke's. He saw Boyle's air pressure research as a chance to test and improve technology, especially air pumps and vacuum systems. Hooke designed and built an improved version of the air pump used for the experiments. So he helped with earlier air pumps leaked or broke easily. So Hooke's engineering skills were vital for getting accurate data. Building his scientific reputation at the time, Hooke was a younger, up and upcoming scientist working under Boyle's guidance. Both Boyle and Hooke believed science should rely on experiments and observation, not just philosophy or theory. Original benefits. Introducing the mathematical formula pressure times volume equals constant, or P times V equals constant. It supported the atomic theory of matter. Boyle's results fit perfectly with the new ideal that matter is made of tiny particles. It inspired other scientists to test new ideals, experiment instead of relying on reason alone. Helped many work fields, but one Boyle is called the father of, and it's chemistry. Modern process. How the experiment is done. A small sealed syringe or piston traps a fixed amount of air. The setup connects to a digital compressed sensor or volume scales. The piston is slowly pressed to reduce the volume of the air inside. And the image on the right is just a little example of it. And I have my own example here to show you. So if you find a plastic bottle around your house, it has to have a screw on. So you take it fully empty, you blow air into it, keep it tight, okay? Then you squeeze the bottle, and you notice it's difficult to compress. I'm squeezing as hard as I can right now. Release the cap, and then press. See how easy it was to squeeze out the air? That's because the cap was keeping the pressure inside. The volume has, so therefore the volume has increased. Modern differences. Expanded applications. The original goal was to study air elasticity. Today, Boyle's law is used in engineering, medicine, aviation, and space science. Modern setups are small, portable, and can be operated by one person on a lab bench. Boyle used a 2-meter glass tube that required an assistant, Robert Hood. Temperature carefully controlled using thermostats are now used nowadays. Back then, he had to try to keep the room at a constant humidity for the pressure, not to mess up his experiments. Modern benefits. Help study lungs and breathing in medicine. Guides design of air compressors, phonionic systems, and spacecraft. Sorry, I messed up on that word. Teaches gas laws and physics and chemistry laws. Improves weather prediction using barometers. Used in industrial machines and everyday devices. Future expectations. Boyle's law may help us with modeling gas behavior in spacecraft and extreme environments, microscale applications in nanotechnology on a lab-on-a-chip device, studying gases under high pressure conditions, advanced computer simulations for engineering and climate research, improve medical devices like ventilators and artificial lungs, in which the artificial lungs is the most intriguing to me because I feel like with conditions that people can get that can help out and improve some people's daily lives that aren't blessed to start out with good lungs. The photo over here on the right also represents the water pressure down the water pressure, the high water pressure underwater.
My name is Joseph Carpenter, and I am going over my original process for Robert Boyle's 1660s experiment for air tube. Boyle and Robert Hertz built a J-shaped glass tube sealed at one end, and they trapped a small amount of air, or some people say gases, in that closed arm. And what they did was they peeled mercury into the open arm to increase pressure on that trapped air. And the measurement of air volume with the mercury were taken. And this showed the result that P pressure versus volume is constant, and that right there formed the Boyles Law. And they used very rudimentary resources that they had back then. Some of the difficulty and complications they had right here is that they didn't have the modern pressure gauge that you see nowadays, and they just relied on the mercury height to determine a measurement for pressure. And getting and to maintain constant temperature was very difficult for them because air expanded or contracted with heat, and they didn't have a surefire way to control that. And glass tube break very easily with mercury pressure, and then air parity and moisture in the air affected the accuracy of their experiment. And then there was also the manual reading factors of human, where they had to manually look at it and had to be like, who knows? Wasn't very precise measurements. But one of the main motivations for Robert and Hertz to do the experiment was to explore the properties of air and verify the ideas of Galileo's and Torricelli's on vacuum and pressure. They wanted to understand how gas responded to compression, and they wanted to establish more understanding and laws of nature. And these steps started leading towards modern physics and chemistry, and they wanted to replace science ideology from alchemy to experimental science. And one of the original benefits of this experiment was it proved how air has weight and can be compressed. It provided a magical relationship with pressure and volume, and then it formed the foundation, the very first thing for gas law. And then it promoted advanced scientific methods. It emphasized experimental science and gaining data from that. And it inspires future works in, for example, pneumatics, engine, and atmospheric science. For the modern method of testing and studying the air and pressure relationship in Boyles Law, nowadays they use precision pressure sensors and digital volume measurement from computers, and they are able to conduct these experiments in extreme controlled temperature environments, and data is collected and plotted automatically by computers or data loggers for some, and they often demonstrate with syringes now, piston, and gas syringes, apparently, I learned that, in labs. And they also utilize the use of like AI, simulation, and computer model that visualize molecular motions under compression. And so some of the main difference with modern approach compared to the original was accurate sensors have replaced mercury comms, computerized data eliminates the human error of reading gauges. The controlled environment that we talked about keep temperature constant, which is one of the main factors of the Boyles Law. There's also safety improvement for scientists, and for example, no toxic mercuries are used anymore. More firm glass are used that doesn't break upon the compression. And then also, in terms of reproducibility, results are very consistent now, and globally they're accepted now and verifiable. One of the modern main benefits now of the modern research into Boyles Law is it is used, for example, like I used with diving, but also aviation to predict gas behaviors under pressure changes. It helped design pneumatic systems out there and internal combustion engines. It's fundamental in medical equipment like ventilators and syringes, and it supports environmental science and meteorology like air compression and expansion, and it's the very basis now for the ideal gas law, which is the cornerstone of modern chemistry and physics. And with that all in mind, the future expectation of the studies of Boyles Law and what people want to get out of it is to continue use in space exploration for pressure controls and habitat or space station and stuff like that, for development of smart sensors for real-time gas behavior monitoring and integration to AI driven simulator to improve efficiency, which we're starting to get there now, and then also potential use in nanotechnology and high pressure material research. And then finally, the law simplicity ensure it remains a teaching and research foundation.